Join me on a fantastic voyage across almost 14 billion light years of space and time, told in unparalleled detail by means of the most dramatic astronomical images ever captured. This is a journey to the edge of space and the very beginning of existence, offering an unforgettable glimpse of the vastness and grandeur of our cosmic habitat. We open with a detailed survey of the Sun, before venturing across the solar system and through interstellar space towards the heart of our galaxy. The shimmering rhythms of stellar life unfold before our eyes. We pass through dense clouds of dust and gas ablaze with newly formed stars amidst the ghostly remnants of others that have destroyed themselves in unimaginable violent explosions. Beyond the Milky Way, we enter intergalactic space. Here we see massive conglomerations of galaxies floating together. Like motes of dust, we see them flock and cluster, forming massive superstructures that span millions of light years, warping space and time with their tremendous gravity. After covering an unimaginable distance of 13 billion light years, we approach the edge of space and the dawn of creation itself. Offering an unprecedented number of extraordinary and beautiful images, Wonders of the Universe brings our cosmos to life as never before, whether casting its gaze on the eerie stillness of massive clouds of interstellar dust, or the colossal fury of supernovas, the gently undulating cloudscapes of alien worlds, or the devouring intensity of stars being ripped to pieces. This is an essential companion for anyone who has ever stared in awe at the heavens. All but 3% of our solar system's mass is concentrated in the Sun. 8 planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, travelling in near circular orbits, account for most of the rest. Planets are confined within a flat disc-shaped region of space, the plane of the ecliptic. All planets apart from Mercury and Venus have other, much smaller worlds called moons orbiting around them. Moons range in shape and scale from about the size and roundness of our Earth's familiar moon to jagged chunks of rock just a few kilometres wide. More than 140 moons have been discovered so far. A ninth planetary world, Pluto, is also small it doesn't count as a proper planet. It is so far away from the Sun that it takes 248 Earth years to complete one orbit. Far beyond Pluto, scattered islands of dust, gas and cometary chunks of ice roam the solar system's dark perimeter. Light from the dwindling Sun travels for at least a year or two before it glints faintly on these last lonely outposts. Beyond that point, the Sun's influences cannot be told, apart from those of the 200 billion other stars whose collective gravity binds the Milky Way galaxy together. Around 5 billion years ago, a vast cloud of dust and gas drifted through our region of the galaxy. These thin, widely scattered wisps originated from the supernova among an early generation of stars. The cloud, called a nebula, was generally pulled around by gravitational forces from other surviving stars in the surrounding galaxy. Most of the atoms in the nebula were hydrogen or helium, but all the other chemical elements were present in smaller amounts. Somewhere within the nebula, a seemingly insignificant clump of matter coalesced, gaining mass until it was capable of exerting its own gravitational force. Extremely weak, yet just strong enough to attract nearby atoms and molecules. This mass, known by scientists as a protostar, grew to the point where its gravity became strong enough to pull in more material from ever greater distances. Tens, then thousands, and eventually many millions of kilometers, dust and gas from the surrounding nebula became concentrated into a spinning plate-shaped structure known as an accretion disk. Within this protostar, our young sun at its centre. Even as the sun gathered mass, some of the debris in the accretion disk began to cluster in miniature and much cooler versions of the protostar process. Small worlds, known as planetesimals, began to form. When these collided with each other and their wreckage combined, these larger structures became the planets and moons that exist today. One of those worlds became the Earth. It began life around 4.6 billion years ago as a hot, chaotic sphere of molten metals and silicates. But over time, the various materials began to divide according to density, with the heaviest metals, such as iron, sinking into the Earth's core, and the lighter materials, such as silica, floating upwards towards the planet's surface. After approximately 100 million years, the outer surface cooled sufficiently for a thin, rocky crust to form. The Sun has burnt for 5 billion years, and will burn for 5 billion more, after which it will have used up a crucial proportion of its available hydrogen. The local star that has nurtured us for so long will turn into a violent and unpredictable monster, prone to sudden nuclear shutdowns and reignitions, expansions and contractions alternating over several millennia. It will end its days as a red giant, so gigantic that its wayward mantle of gases will swallow up half the planets of our solar system, including the Earth. Mercury and Venus will simply vanish. Everything on our planet that lives and breathes will be utterly vaporized. The grass, the trees, even the toughened lichen that cling to granite will be blasted into atoms. The oceans will boil away to the last drop. The ice caps will vaporise. The sand on every beach in the world will fuse into glass. If Earth survives at all, it will do so only as a scorched lump of rock. Fortunately, this disaster lies so far in the future, there is no point to worry about it. In the 4.5 billion years since its birth, the Sun has converted 4 million tons of hydrogen into energy every second. The amount of available hydrogen is still so great that it should be able to sustain this process for another 500 million years. In the Sun's core, immense gravitational pressure squeezes hydrogen nuclei together until helium is formed, in a process known as fusion. The mass of helium that emerges from this process is 0.7% less than the mass of hydrogen that goes into it. That missing mass is liberated in the form of heat and infrared energy, ultraviolet and visible light, and a small proportion of X-rays and radio waves. What we call sunshine takes a mere 8 minutes to reach as far as Earth. Temperatures in the Sun's atmosphere, known as the corona, are at least 2 million degrees centigrade, far greater than those at the Sun's surface, the photosphere. The corona is threaded with powerful and fast-changing magnetic fields that constantly twist and distort into new patterns. Positively and negatively charged subatomic particles spiral at very high energies along the magnetic field lines. Vast clouds of electrically charged subatomic particles are continually blasted away from the Sun. These violent bursts, which often eject the equivalent of 20 billion tons of matter, are properly known as coronal mass ejections, CMEs. The swarm of particles travel across the interplanetary space, interacting with all the planets and moons in the solar system, including the Earth. The powerful electrical charges in the solar wind can disrupt computers, interfere with national power supplies, and totally destroy the circuitry of orbiting satellites. Sunspots, the familiar dark-looking blemishes on the Sun's otherwise bright disk, are concentrated regions near the surface where magnetic fields become extremely strong. Sunspots usually last for several days, although large ones may survive for several weeks. Sunspots can be seen when the eyepiece end of a telescope is focused onto a sheet of white paper, but only a fool would actually look into the telescope. All through recorded history, we humans have known the cost of staring directly at the Sun. On a clear afternoon, the Sun is a dazzlingly bright disk of featureless white light. So bright we cannot safely look at it with the naked eye. A closer look through strong filters shows the Sun's spherical shape and its complex and ever-shifting structures, such as solar flares and sunspots. Solar storms, coronal mass ejections, or CMEs, can hurl more than 100 billion tons of mass into deep space at speeds of millions of kilometers per hour. The ejected mass is in the form of subatomic particles. When these reach the Earth, they interact with the planet's upper atmosphere and magnetic field. Solar prominences. Vast curling clouds of relatively cool plasma can easily be seen through a telescope with a suitably dense filter to shut out the glare. Unlike CMEs, these visually dramatic prominences are usually confined within the Sun's atmosphere, the corona. Sunspots. The photosphere is the obviously bright surface of the Sun. It is often dappled with sunspots, created when huge and powerful loops within the Sun's magnetic field force their way through the photosphere. The heart of a sunspot. This extreme close-up is one of the sharpest images ever obtained of a sunspot. It reveals features as small as 100 kilometers, or 60 miles, across. Dark, thread-like cores of plasma run the length of the bright filaments, all shaped by the restless rearrangements of the magnetic field. Solar grains. An image taken in extreme ultraviolet light reveals a seething mass of dark cells, a phenomenon known as granulation. Each grain is about the size of Texas. Granulation is caused by convection currents inside the sun. Hot material rises into the photosphere, then cools down. If anything on the sun can be called cool, and falls back around the edges of each cell. An Earth telescope captured the International Space Station silhouetted as it passes in front of the sun. The station's shadow is not to scale with the sun, because the station orbits very close to the Earth. The intersection lasted just fractions of a second. Careful timing was needed to capture this shot. Solar eclipse occurs when the moon interposes itself between the sun and the Earth, temporarily obscuring our view of the sun. By a lucky coincidence, the moon's disk neatly superimposes over the sun's disk during a full eclipse, leaving just the corona visible. Energetic threads, suspended by magnetic fields above an active region of the photosphere. These bright filaments span more than 40 times the diameter of Earth. Such filaments are unstable and intermittent. The scene was captured in extreme ultraviolet by the Solar Dynamics Observatory, one of many space-based systems monitoring the sun. Jets on the sun. Imagine a pipe as wide as Arizona and as tall as the Earth. Now imagine this pipe filled with hot gases moving at 50,000 kilometers or 30,000 miles per hour. Think of the pipe made not from solid material, but just by a transparent magnetic field. This is a spicule, one of thousands constantly generated by the sun. Spicules last for around 5 minutes, then fade. The magnetic sun. This image, taken by the Solar Heliospheric Observatory satellite, shows gas at different temperatures and various frequencies of radiation emanating from the sun, along with a tangle of twisted streamers and prominences reaching into the corona and beyond. We are a long way from fully understanding how the sun's magnetic field shapes its complicated behaviour. And that concludes today's episode. If you did find this informative or useful in any way, we would really appreciate if you hit the like and subscribe button and the notification bell to get alerted when every episode is uploaded. Thank you very much for watching. Take care. Peace, everybody.